Okay, so we have this problem. Gate AB extends 1.2 meters into the page, mass of 180 kilograms, and is hinged at point A. Both the glycerin and the water are at 20 degrees Celsius. Water is continually added to the right side of the tank. At what height H will the normal force at B be reduced to 0? Okay, so I'm going to start off by drawing a free body diagram of the gate. And I don't know why this is so thick. Change that. Okay, so my free body diagram for the gate AB. Okay, so here B we are going to have a normal force. Normal. We are hinged at A, so that means we will have this AY and AX. We know it has a weight of mass times gravity. Okay, and then, so for this glycerin, we are going to have a gradient of pressure. So as we get deeper, the pressure is going to increase. Pressure increases with depth, and that's just basic science. So the pressure is going to be this little gradient, and it'll increase with depth. Same thing with the water. So these should be relatively decreasing. So as a result of these pressure gradients, we are going to have two resulting forces. And these resulting forces, so if I have my gate here, this is the centroid right here. This is the middle of the gate, right? Same with where the placement of mg is. This is the centroid. My resulting force for glycerin and for water has to be below the centroid, and this is because the pressure gradient increases with depth. So it doesn't make sense if it's above the centroid or at the centroid because the pressure is greater at the bottom. So we can assume for this resulting force, I'm going to call FL, to be somewhere below the centroid, and then this force on the right to be somewhere right there. Now we're not exactly sure where the position of these forces are, but that's what we will be solving for. However, we can assume that number one, they will be below the centroid, and number two, that one of them is going to be greater than the other. We just have to go ahead and solve to see. So I'm going to add these forces here, and these are going to be perpendicular to the surface. I didn't draw that too great on my picture here, but they are perpendicular. So this is FL, whoops. And then this is going to be FR. Again, we don't know their magnitudes, but we will be solving for that. Okay, so that is everything for my forces. I am going to go ahead and label some dimensions. So first of all, we don't know where these forces are going to end up at, so we are going to name it a distance. So this is going to be the position of this resulting force on the left, from there to there, and then this will be the position of this resulting force on the right, YRR. Okay, that's something that we will have to solve for. We don't know that value yet. And then, so I forgot to include, well, I'll go ahead and draw on this side. So then I'm going to add some other dimensions. I'm going to go ahead and draw them on here. So I have this height from the centroid, height, how do I say this? Height from the centroid to the free surface of each side. So at glycerin, this triangle obviously represents a free surface. So the height from here, the free surface, to the centroid, height from the centroid of glycerin, that's going to be that. And that's going to be that distance. And then this height to the centroid from water, from the free surface. So height of the centroid, water. Okay. And then we are going to have this position of the centroid relative to the top of the gate. So that's going to be y sub c from the top of the gate to the centroid. Let me make this thinner. Y sub c. Okay. Is there anything that I missed? No, that looks good to me. Okay, so then I have my free body diagram here and my dimensions labeled. I am going to start off by solving for the forces. Okay, so we do not know the force on the left due to glycerin. However, we do know that because it is pressure below a surface, below like a body of liquid, and it is going to have, we are going to use this equation of the specific gravity, oh my god, gamma, the height of the centroid for the left would be glycerin, times the area. Okay, so the specific specific gravity, no, none of the above. Specific weight, gamma represents specific weight. I think that's gamma. Okay, besides the point. Anyways, this specific weight, and this specific weight value for glycerin I found in the textbook to be 124,000, and I converted it to newtons. In the book it is in kilonewtons, but I converted it to newtons. Newtons per meter cubed. Okay, the height of the centroid from the side of glycerin. So we have this total depth of 2 meters. However, that is well beyond the centroid. So we need to subtract the distance to the centroid. So the distance to the centroid is going to be 2 meters, right? This entire depth of 2 meters minus, and we want this height of the centroid. So there's essentially a small triangle here. The entire meter of the gate is 1 meter, so this length would be 0.5 meters, and then we have this angle of 60, so that's the triangle that I'm referencing, 60 degrees. So it is going to be 2 meters minus 0.5 sine of 60, and this is in meters. And then the area of the gate, actually let me include that meter into here. Okay, the area of the gate. So they did give us that the gate AB extends 1.2 meters into the page, and then we have this horizontal length or diagonal length of 1 meter. So it's going to be 1.2 meters by 1 meter. Okay, and now we can solve. So solving through, we should get, let me just double check, 2 minus 0.5 sine of 60 times 1.2. Oops. Okay, so we get this resulting force of 233,167.7 newtons on the left. And I'm going to go ahead and do the same for the right. So the force on the right is going to be equal to the specific weight times the height, what is the official name for this? The depth below the surface to the centroid, yes, area. And this is for water. So the specific weight of water, again, is 9.8 kilonewtons per meter. I converted to newtons per meter cubed. The height below the surface to the centroid. So we actually do not know that because we have this value h. So same thing with the glycerin, we have the entire depth. So we're going to have to subtract the length to the centroid. So it's going to be h minus, and the length, the vertical length is 0.5 sine of 60. This is in meters. And the area is going to be 1.2 meters squared. Okay, so solving for that, I do get 11. Okay, so before I actually solve for that officially, I'm going to go ahead and redefine the value. So I'm going to have this new h, and this new h is going to be equal to the quantity inside of here, just to make it easier, and then at the end I will go ahead and plug that back in. Okay, so then we're going to have 11,760 times this h, and this is newtons. Okay, so I have this value, Now I need to find the positions of each of these resulting forces. So starting with the one on the left, y, oh my god, y sub y sub RL, y sub RL. Okay, so we have this equation given, Ix sub c divided by y ca plus yc. Okay, Ix sub c I can solve for separately because it is going to be the same value for both of them. So I'm just going to solve it right here on the side. The moment of inertia of the centroid, so it's going to be 1/12 the base times the height cubed. In this case, we are going to have to use sine theta because we do have this angle of 60 degrees. Let's scroll up. This angle of 60 degrees right here. Okay, so it's going to be 1/12 the base, which is 1.2 meters, the height, which was 1 meter cubed, times sine of 60. And that'll give us the value of, I'm just going to leave it as 0.1 sine 60 meters to the fourth. Okay, and now I'll be using this value to find both the position of the left and the right resulting forces. So plugging this back into this equation, we will have 0.1 sine of 60 meters to the fourth divided by y sub c. So y sub c is going to be the distance of the force. Okay, so this side of the equation is going to be the force. It's correlated to the force. The resulting force that we get from glycerin or water, whatever it be. And then this is going to be the position for the moment of inertia. Okay, so for YRL, we'll have y sub c is going to be so we found y sub c to be the entire distance, which is going to be 2 meters. So in this case, what I mean by force and inertia is that the first y sub c is going to be the length. It's essentially going to be y sub c g. And then y sub c, the other y sub c is going to be this y sub c right there. So one is going to be what causes the force, so the entire length, and then this one is just going to be what causes the moment of inertia. Okay, so 2 minus 0.5 sine of 60 meters times the area is 1.2 meters squared. Okay, so now using this value, I should have 0.1. Oh, I forgot to add the 0.5 meters. So the y sub c is going to be, so we have this entire length of 1 meter, so y sub c is only going to be 0.5 meters. And actually, let me redefine this y sub c, because it should not be in the positive y, it's actually going to be along the gate, so it's going to go like this, y sub c. And that's just the length to the centroid, which is just going to be 0.5 meters. So that is meant to be a little bit slanted, not upright. My mistake. So we're going to add 0.5 meters. And that's just the position to the centroid. Okay, plus 0.5. And we should get a value of 0.546 meters. Okay, so this is our third value that we have solved for, that we are going to use. Let's go to, how do I add another page? Page. Okay. Whoops. I'm not too sure. 1 second. Okay, so now that I have that, I'm going to go ahead and solve for y sub, okay, why is it doing that? I love and I hate technology. Y sub r and the r. Okay, same thing, same equation. I sub xc divided by y of c a plus y sub c. Okay, and then again, this y sub c is essentially the h sub c of the relative glycerin or water, and that's divided by the sine of 60. Okay, so we have 0.1 sine of 60, that's the value for the moment of inertia, meters to the fourth, divided by y sub c. In this case, I had defined, again, scrolling back, h to be h minus 0.5 sine of 60, so I'm just going to go ahead and plug in that h, that new h that I redefined, and then the area is 1.2, what the heck, 1.2 meters squared. And I'm going to add, again, 0.5 meters, which is the position from the gate to its centroid. So solving for that, we get 0.0722 divided by h plus 0.5, and this whole value is in meters. Okay, this is our fourth value that we are going to utilize. And then at this point, we are just going to go ahead and solve for the moment about A. So the sum of the moments about A. So we're going to have a moment due to each force. So a moment due to the resulting force on the left. And I'm not writing this relative to the positions just yet. Actually, I'll just go ahead and write it relative. So the left is going to produce, I'm going to define positive to be counterclockwise and negative to be clockwise. So the force on the left is going to produce a counterclockwise moment minus the moment, what the heck, minus the moment Fr plus the moment due to the weight plus the moment about B. Okay, so we only will have one negative value here. Reading back the beginning of the problem statement, they're asking at what height h will the normal force at B be reduced to 0. So we want the normal force at B to be 0. So I'm going to go ahead and solve for this as if B were 0, because that's what we want. So that's good for us because one less moment that we have to solve for. So plugging this in, I'm going to start with the weight. So 180 kilograms times 9.8 meters per second squared times 0.5 sine 150. Here, this is just the weight, force times distance times the sine of the angle between them, which I found to be 150 degrees, minus 11,760H, the force due to the right, times its y sub r, which we found to be 0.0722, those are 2's, divided by h plus 0.5 meters. Okay, this is Newton meters. This weight will be Newton meters. And then we're going to add the left. So the left is going to be 0.546 meters, which is the distance times the force, which was 23316.7 newtons. Again, Newton meters. Okay, so here we will get 441 Newton meters minus 849.072 Newton meters minus 5880H, and all I did here was distribute this 1760 to that, which will cancel the H's, and then distribute it to the 0.5, which will leave us with 1H plus 12730, and this is all equal to 0. So solving through, I do get a value of H equals 2.09 meters, but again, remember that I redefined H, so I solved for this new H, so H is actually equal to H minus 0.5 sine 60, so this H, 2.09 meters, is equal to H minus 0.5 sine of 60, and again, I just did this for ease, but you could have solved through, I just chose not to, so it's going to be H equals 2.09 meters plus 0.5 sine of 60. Okay, sorry for my tail writing. My writing is actually a lot nicer than it is on this tablet. So we do get 2.52 meters for this height of water. Okay, so just sort of walking through what I did. I just went ahead and I labeled all of my new distances as well as the resulting forces from the left and the right. I went ahead and drew a free body diagram. I solved through for the left force using the specific weight times the height to the center of gravity from the free surface of glycerin times area, and then from there I did get a value. Again, I did the same thing for the right side, specific weight times the height from the surface to the centroid times area. Here we had to solve for H, or we had H as part of the answer, and then again I redefined this H to be here, H equals H minus 0.5 sine of 60. Then we went ahead and solved for the position of the resulting force on the left using the equation given. We did have to include sine of 60 for the moment of inertia because we had this angle here. And then we added 0.5 meters. So again, the top was the inertia and then the bottom is the distance from glycerin to the height of the centroid. Times the area, and we added this 0.5 meters, which is this y sub c right there. And then we got a value. Same thing for the side on the right. Here we did have h in the answer because we are solving for h. And then I went ahead and I solved for the moment about A and making the moment about B equal to 0 because that's what the problem is asking us for. I went ahead and solved for all my moments, including their directions. So the moment about the right side is going to give us a clockwise moment. So solving for that, I got h equal to 2.09 meters. But I did define my h to be h minus 0.5 sine of 60. So solving for my original h, I found it to be 2.52 meters. And that is the height that the normal force will be reduced to 0. Okay, thank you. Oh, let me go ahead and sign my name. And my name is Isabel Murguia. Thank you, Professor. Have a good weekend.